All right, so this is mastering problem 6.15 about the cheetah cornering, and I would agree this is an impressive cornering maneuver, 16 meters per second squared. The most immediate thing you might notice about that is that it's about 1.6 Gs, and when we get around to the answer for this question, you might have a moment where you're like, huh, I probably could have answered that to begin with, because you might just kind of think, you know what, if I had a friction coefficient of 1, I could accelerate at 1 g. So to accelerate at 1.6 g's, I'm probably going to need a friction coefficient of 1.6. But let's do some proof with Newton's laws to deal with this. So I'm not going to attempt to draw a cheetah, but I will draw a force diagram for the cheetah. So as the cheetah is going around, we're going to assume that this is a flat curve that the cheetah is cornering around. There will be a normal force on the cheetah, there will be a gravitational force on the cheetah, and there will be a substantial friction force. And we're going to assume that the cheetah maintains, and they do ask the coefficient of static friction, we're going to assume that the cheetah is not sliding as it's doing this cornering maneuver, even though it's quite possible the cheetah could occasionally slide while doing said cornering maneuver. Now, if you think about this, level surface, normal force, gravity, they're going to balance out, so those will not contribute to the net force. However, the static friction force will contribute to the net force. And since this cheetah is going around a curve, and the only kind of circular motion we know how to calculate is uniform circular motion. We're just going to assume that it's undergoing uniform circular motion. So for uniform circular motion, we can say that the net force equals the mass times v squared over r, which is actually not going to be particularly helpful to us in this one. I think what we need to do here is just mass times centripetal acceleration, because they gave us the acceleration of the cheetah. They didn't give us the mass and the velocity and the radius of the turn. So I think where I'm going to go with this is just approach it with a static friction equals m times AC kind of approach. And remember, AC equals v squared over r, so that this is valid for us to do. Now, static friction, hopefully you remember, is calculated with Fs equals mu s times normal force. And so I'm going to take this and replace static friction with mu s times normal force. And that equals MAC. And from the force sum over here, I guess I should have specified sigma F in the, we'll say, X direction. And then over here in the Y direction, sigma F Y equals, they're the same size in opposite directions, 0, they cancel out. And that equals normal force minus mg. So what we can take away from that is that the normal force, at least the size of the normal force, equals m times g. And knowing that, I can replace normal force with m times g. Okay, and look at that. Mass cancels out. You divide both sides by m, and the m goes away. And we want to know the coefficient, so we're going to end up doing mu s equals AC divided by g. So our cheetah going at 16, or accelerating at 16 meters per second squared, and mastering loves 9.8, so we're going to do 9.8 meters per second squared, and that'll give you somewhere around 1.6 as your coefficient. Also notice that the units cancel out, they're both accelerations. That's okay, because coefficient of static friction is supposed to be a unitless quantity, so that will give you an acceptable answer. Hope that helps.